Hello, everybody. This is Homer This is Homer White with the beginning of a series of screencasts for Chapter 8 on regression. This screencast covers sections 8.1 and 8.2 in the textbook. We're going to be looking at fitting a regression line in a situation where we're examining the relationship between two numerical variables. So you're going to need tiger stats as usual. First of all, a little review from your algebra classes in high school on lines. So you're familiar with, y equals mx plus b slope-intercept form for the equation of a line. Here is a very simple line whose equation is y equals 1 plus 2 times x. Here's the x-axis, here's the y-axis, and the blue is the graph of the line. Now you might be used to thinking of it as y equals 2x plus 1, the mx plus b form. And in statistics, we tend to put the intercept first, and then the slope times the x variable second. So y equals 1 plus 2x. The y-intercept is at the level 1 here. And then we have this slope of 2 multiplied by the x variable. Now just a reminder of how that slope comes about. The slope of a line is its rise over its run. And the slope of this line is 2 if you were to run over 1 unit on the x-axis, like from x is 1 to x is 2, you would have to rise up 2 units along the y-axis in order to stay on the line. So if you start here at the point where x is 1 and y is 3, if you increase the x 1 unit to where now x is 2, you're going to have to go up to where the y is a 5 in order to stay on the line. That rise over run, 2 over 1, is the slope of the line. Okay, let's take another line. This one has the equation y equals 3 minus a half times x. The 3 is the y-intercept. When x is 0, y is 3 up here. And the slope is a minus half. Let's take a closer look at that slope. Say you started at this point on the line where x is 1 and y is 2.5. And suppose you ran over 1 unit along the x-axis to where the x is 2. Then this time you'd have to fall in order to get back to the line, and you'll have to fall half a unit to where the y is now 2 instead of 2.5. So we say the rise is negative a half. And again, the rise over the run is that slope you see for the line here in front of the x variable. So in both cases, what we have noticed is the following. If the slope of the line is a b, now some number b here in front of the x, then whenever you increase the x by 1 unit, you're going to have to change the y by b units to stay on the line. I say change because if the slope is positive, you'll have to increase y to stay on the line. If the slope is negative, you're going to have to decrease y to stay on the line. But either way, you're going to have to change it. And the amount you change it by is that b amount. So a way for you to just interpret the slope for yourself is this, that the slope of a line tells you how much y changes when x is increased by 1 unit. Okay, let's next go back and just review stuff we learned earlier in the course about how we investigate the relationship between two numerical variables. Our tool of choice was scatterplots. So for example, here's some old data from where every point here on the scatterplot is a pair of people, a father and his son. And the position along the x-axis for the point is the father's height. So for this point here, that's a pair of people. The father was 65 inches tall. The son looks like about 62 and a half, maybe 63 inches tall. Or in this pair, the father was 70 inches tall and the son was, looks like about 79 inches tall. Overall, the cloud of points, the cloud of father-son pairs, rises as you go to the right. And that means that the taller the father is, the taller the son is. If you've got short dads down here, you look at their son heights, and they tend to be kind of lower on the y-axis. Tall dads are over here, and you look at their sons, and they're higher up on the x-axis. The taller the father, the taller the son. That's a positive linear relationship. Here's some artificial data that illustrates a negative linear relationship. The bigger the x value is, the lower the y values are. You can also have relationships between the x variable and the y variable that are not linear. For example, here we have a curvilinear relationship. When x is small, y tends to be big. When x is kind of medium-sized in the middle here, y tends to be small. And when x is big, y is getting big again. So that's totally a relationship between x and y, but it's not a linear relationship. Here's some real data where every point is a household during a billing period. And on the x-axis is the average temperature in degrees Fahrenheit outside during that billing period. And on the y-axis is the gas bill for the household. And what we see is that at higher temperatures, the gas bill was lower because they weren't having to, use gas for heating and stuff like that. Now, the overall pattern is negative, but it's not negative linear because you can kind of see a bit of curvature here and some flattening out, at the end. And then in this artificial data, there's no relationship at all between the value of x and the value of y. The cloud of points doesn't rise, it doesn't fall, it just looks like a random cloud. When x is small, the y's vary. When x is big, the y's vary the same amount, There's no difference how high or low the variability is. No relationship between x and y. Linear regression is a way of putting numbers to those visual pictures that we've got through the scatter plot. So the question I've got for today is, when the relationship is linear, when the cloud of points does seem to follow a line, could we find the line that the points appear to follow? Could we find it mathematically, like get its equation? And could we use that line to predict the y value for some new observation whose x value we happen to know? This subject, where we answer these questions, is called linear regression. So, to give us an example data set to start with, let's learn about the stumps data. It comes from the package TigerStats. So let's do a view and help on stumps in RStudio. And so you can read about stumps here in the help, and we can take a look at the view in a minute. Here's the situation. We know that there's kind of a symbiotic relationship between the various species in an environmental habitat. And we're wondering, if beetles get some benefit from the activity of beavers near a creek or a river, where the beavers, they gnaw down trees and leave their stumps. Do beetles get attracted to these stumps? Because after all, what happens when the beavers gnaw down the trees is that the stumps try to put forth new growth. They sprout out these tender green shoots, and beetles are able to eat them. And so, maybe beetles congregate where these stumps are and get some benefit out of them. How could you measure or detect that? And so the biologists, in one experiment, they marked out 23 circular plots, and every row of stumps is a plot. All the plots have the same area, and they were all lying along this creek side. And in each plot, the researchers counted the number of cottonwood stumps, left over from the beetles, from the beavers gnawing the tree down. And they also went through the plot and counted the number of clusters of beetle larvae that they found there. So like in this first plot here, there were 2 stumps, and the biologists counted 10 larvae clusters. And in the next plot, there was 2 stumps, and the biologists counted 30 larvae clusters, and so on for all 23 of these little plots. And what they're wondering is, do we get evidence here from the data that there tend to be more larvae clusters in plots where there are more cottonwood stumps? And if there is there a way that we could predict how many larvae clusters we would find in a plot where we can count the stumps? So let's go ahead and make a scatter plot, and I'm just going to run this in RStudio to give you an idea. But before I run it, remember our target is a scatter plot, so we say GF point. And I'm going to think of larvae as the response variable, because I'm thinking maybe the number of stumps helps to explain, how many larvae might be found there. And I'll think of stumps as the explanatory variable, so it's going to come second after that twiddles. And of course, you have to say where those variables live, and it comes in this data frame called stumps. So let's go ahead and try this out in RStudio, as you should always do when you're following along with one of these discussions. Give it a try, see how it works. Yeah, so there's our plot. And there's my Facebook page. And my email. Where is my... There we go. So here's our plot. And the cloud of points does seem to follow, a rising line. I'm kind of drawing it with my mouse. That's the line I imagine in my mind. So what I'd like to do is set up kind of a mathematical model for the situation, a model for that line. What we're going to imagine here is that the number of larvae clusters is a linear equation, a number, beta naught, plus another number, beta 1, times the number of stumps in the plot, plus another number that's that's produced by random chance. The beta naught's the intercept. And we don't know what it really is. The beta 1 is the slope, and we don't know what it is. Now, if the beta 1 were 0 here, if that number beta 1 were 0, then no matter whether the number of stumps is large or small, the product here would be 0. And so the number of stumps wouldn't be able to have any effect on the number of larvae clusters. The number of larvae clusters would just be this beta naught number plus the chance variation, in how things work out in a plot. The number of larvae is not totally determined by the number of stumps after all. It's determined by all kinds of chance variation in which beetles wander around, what places they find to go, whether or not the beetle is able to reproduce before it dies. And so the number of larvae is not a fixed determinate thing, even if it's related to stumps. There's always chance variation that comes in. But if there's no relationship with stumps, that beta 1 would be a 0. On the other hand, if the beta 1 is not a 0, if the slope of this little line here is not a 0, then the stump variable is related to the number of larvae clusters. So how do we investigate what that unknown line might actually be? We do it with a function called lmGC, okay? And you run it, the code looks just like making a scatterplot. Response variable twiddles the explanatory variable, data set where those variables live. But if you want to see a picture of the line that we're going to produce, you say graph is true. So let's give this a try in RStudio. And so you get some output to the console that we're going to examine bit by bit. And you get your scatter plot over here in the plot window, same data points, but that blue line is what we call the regression line, and we're going to talk about it for a bit too. So first of all, this graph, we've got this regression line here in blue called the linear fit up here in the title. Sorry about that. And that line is our best guess right now based on the data for what this little equation right here would be. Beta naught plus beta 1 times stumps. We don't know the y-intercept here. We don't know the slope here. But this blue line does have a y-intercept, and it does have a slope. And that y-intercept and that slope are our best guess at the unknown beta naught and beta 1. So we'll need to look in to see what they are. The equation of the regression line comes in that output to the console, and it's right here. The larvae is on the y-axis. The stumps is on the x-axis. So what we're talking about here is an equation y equals negative 1.2861, that's the y-intercept, plus 11.8937 times stumps times the x variable, and that's the slope. So the y-intercept of the regression line is our best guess at that beta naught number, and the slope of the regression line is our best guess at that beta 1 slope number for that linear model. And this slide summarizes what I just said, but with a little extra notation. And so this little number here is technically called beta naught hat, okay? Means it's trying to estimate the unknown beta naught. That should actually be a negative 1.2861 here. I should fix that. Anyway, we hope it's pretty close to the unknown beta naught. And the number here, the slope estimate, is called beta 1 hat. hat in statistics means you're trying to estimate an unknown parameter. So we hope that's pretty close to beta 1. Now, interpreting the slope of a regression line is very important. And to figure out how to do it, you fall back on what you remember from algebra and what we just reviewed. The slope of a line tells you how much y changes when x is increased by 1 unit. So when we look at this regression line that we've got, we could interpret its slope like this. For every additional stump in the plot, that's increasing the x by a unit, the predicted number of larvae clusters increases, see that's the change in the y, by about slope. And so, looking back at that graph, every time you move the number of stumps up by 1, say from 2 to 3, then your position on the y-axis when you're at this line, it goes up. And the amount that it goes up, from this level to this level, is the slope of the line. It's that 11.9 thing. So that's a great way to interpret the slope of your regression line. Now, another way of thinking about it is to imagine you have two plots that are the same in every way, except that one of them has one more stump than the other, like one of them having 2 stumps and the other having 3 stumps. Then the plot with the extra stump is predicted to have about slope more clusters, 11.8937 more clusters. And so one of the things that you'll practice with in the DA is how to articulate, write out sentences like this that tell people your understanding of what the slope is telling us. The y-intercept can be interpreted too. It's just usually not very important to do it. The y-intercept is what the y value is going to be when the x value is 0. Like when there's no stumps, then you get out here a 0 for this term. And so the regression line would be at level negative 1.28. And so if you interpret that in words, it's saying if a plot has no stumps, then the linear model predicts that there'll be negative 1.2 larvae clusters in it, which is kind of silly. You can't have negative larvae clusters anyway. And so usually the intercept is not very interesting to us to interpret. Now there's more to the output here. Let's head back to RStudio. We've got that equation of the regression line. We've talked about it, but there was this bit about correlation coefficient up here, and there was this other stuff, residual standard error and R squared, and we're going to get to that as well. Let's handle the residual standard error first. It's called S for short because it's a lot like a sample standard deviation. When you make a prediction about a new plot, say there's some other plot that's the same area as all the plots in the study, but it wasn't included in the study, but say you knew how many stumps were in the plot and you wanted to predict, using the regression line, you wanted to predict how many larvae clusters you would find if you searched through it. The regression line could help you predict, like you could go, just head back to RStudio and zoom in. Say that you had some plot with 3 stumps. And you could go to 3 here, and you could go up to the regression line and go over. And that level, which is like about 33 or so, would be your prediction. You predict about 33 larvae clusters in that stump. But in the actual study, you didn't always get 33. You got 33, give or take some for chance variation and how things work out with beetles and larvae in along a river. And so you'd like a give or take figure to go along with your prediction. And the residual standard error is a rough give or take figure. And so you could say, well, I predict about 33 larvae clusters, give or take, 6 clusters or so. So here's another working out of the same example. Say that your plot has 4 stumps. Say this new plot has 4 stumps. Then, you could go to the regression line, and you don't have to rely on the graph. You could use the equation. And here's the equation, the regression line, but you're just plugging in 4 for the x, and you get 46.28. And so you would predict to find 46 or so larvae cluster in that plot, but your prediction could easily be off by the 6 or so. So that's how you use the residual standard error in your mind. Now you can actually get a little better idea of the give or take figure, because the give or take figure, there's stat theory that helps you know that the give or take figure actually isn't the same for every value of stumps. It varies from value to value. So to get it, you can actually do lmGC, but go ahead and store the results in a variable. I'll just call it mod for model. And then there's an R function called predict, and you can run it on that model where you say, okay, got my model with my regression line in it. Let me make a prediction when there's a new plot that has 4 stumps in it. And so if you were to try this in RStudio, and you get this response down in the console, let's take a look at it. It says we predict the number of larvae clusters is going to be about 46.29, give or take 6.863 or so for chance variation. So it's a little different from the residual standard error. And if you try out different numbers here for the stumps, you'll get little bit numbers here. But they'll all be kind of around the residual standard error. Another piece of the output in the console for lmGC was correlation coefficient. So let's talk about that. Correlation, which is often denoted R, is a numerical measure of the strength of a linear relationship. So you got strong linear relationships and you got weak ones. Strong ones are where there's very little scatter around that regression line for the points, and weak ones where there's a lot of up and down scatter. Well, the math fact about the correlation coefficient is that it's always between -1 and 1, no way out of it. And the closer the R is to 1, the stronger you'll see that linear relationship being when you look at the scatter plot. And it'll be a positive linear relationship, a rising cloud of points. Now, the closer R is to -1, the stronger the negative linear relationship is. And if the R is around 0, then there's really no linear relationship there. And so, as an example, here's just some artificial data where there's a pretty strong linear relationship here. The cloud of points, stays pretty close to the line. There's not a lot of up and down scatter away from the line. Strong positive linear relationship, and look at the correlation coefficient. It's really close to 1. Here's a positive linear relationship, but it's weaker because there's a lot more up and down scatter, Look at the R. It's positive, but it's not so close to 1, indicating the weaker relationship. Here's a pretty strong negative relationship, not much scatter, and look at the R, pretty close to -1. Here's a weak negative relationship. The cloud of points falls, but there's a lot of scatter. And look at the R. It's negative, but it's not all that close to -1. And here's a situation where there's essentially no relationship. I've forced R to draw a regression line, and it made its best guess, and it rises slightly, but really it just looks like a random cloud of points here. But look at the R. It's just like close to 0. So that's how the correlation coefficient can work for you. It kind of goes along with what you see in the scatter plot in terms of those linear relationships. So in our stumps data, the correlation coefficient R was 0.916, which is fairly close to 1. And so that backs up what we saw in the scatter plot. There was a positive linear relationship between stumps and number of larvae clusters, and it was a fairly strong one as well. Now, another piece, and the last piece of information that comes with lmGC, is the unadjusted R-square down here. So what's that about? Well, R-square, unsurprisingly, is the square of the R number. The R number was like 0.916. If you were to square that on a calculator, you'd get 0.8391. And there's a cool math fact that R squared gives you the percentage of variation in the Y values in the data that's explained by variation in the X value. So, back to this scatter plot again. The number of stumps varies. The number of larvae cluster vary. But it seems like the variation in the larvae clusters is partly explained by the variation in how many stumps there are. Because this line rises, small y values here, big Y values here. But it's just partial. Because, varying the stumps from 2 to 3, although that leads to generally higher larvae clusters, there's still some variation just within, all the stumps being 2 or all the stumps being 3. So varying the stump number doesn't tell you all the variation in the larvae cluster number. It only partly accounts for it. Well, that R squared number actually puts a percentage on it. 83% of the variation in the larvae cluster values in our data can be accounted for by the variation in the stump numbers, from the 1 to the 5 stumps. Since R squared is the square of R, it's always going to be between 0 and 1. And the closer it is to 1, the better the regression line is going to do at predicting Y values off of X values for new observations that weren't in the original study. Now, you might be wondering, how does R find the formula for its blue regression line? Where does it come from? So I'll give you a little background. Let's say the points on your scatter plot are mathematically denoted x1, y1, x2, y2, x3, y3, x4, y4, all the way up to maybe xn, yn, where there's n points on the scatter plot. And so maybe here's an example where there's 10 points on the scatter plot. x1, y1, x2, y2, all the way up to x10, y10 up here. Okay? Now, for each I, where I ranges from 1 to n, so in our little example here, I would range from 1 to 10. Let's let yi hat denote the height of the regression line above the value xi on the horizontal axis. So the yi hat is that's the height you go up to from xi in order to get a prediction for y values. Yi hat is what the regression line is going to predict that y is when the x value is known to be xi. So let's look at a picture of that. So I've got my same points on my scatter plot here in black. Same x1, y1 through x10, y10. But I've drawn the blue regression line as well. And along the regression line, I've got these points where the y coordinate is the height of the regression line, right on the regression line. It's the yi hats. The height of this point is y1 hat. The height of this blue point is y2 hat. The height of this blue point is y3 hat, y4 hat. And the height of this point is y5 hat. Its coordinates are x5 and y hat 5 or y5 hat. Okay, next step. For each I from 1 to n, there's a quantity we call the residual. And it's the actual y value in the data, yi, minus that height of the regression line value, the predictor value. Okay? It's the difference between the actual value of y and the value that the regression line would predict if you used it. So what I've drawn here is a little picture that gives you an idea of the sizes of the residuals. And I've color-coded them according to whether they're going to be negative or positive. So the turquoise here is positive, the red's negative. Look at this first point. The black point up here is the original data. It lay above the regression line, okay? So the yi, the actual height, minus the y1, the actual height, minus the y1 hat is a positive number. The residual is positive. This is another positive residual. Here's a negative residual where the y3 is less than the y3 hat. The y4 is less than the y4 hat. And here's like the biggest residual we see where the y5 was less than the y5 hat. And so on for the other 5 points. There are 5 residuals that go along with them. Okay. Now, if you were to take each of the residuals and square them, then all of those numbers would become positive, because when you square numbers that are negative, they become positive. And if you were to add them up, all of them, then you get what's called the error sum of squares. Sometimes that's abbreviated SSE, error sum of squares. And this number measures how much the actual y values in the data differ from the values predicted by the model. You know, the closer those yi's are to the predicted value, the smaller the difference is, so the smaller the square will be, so the smaller the sum would be. Now, there's all kinds of lines that you could have drawn through that data. You know, like one could draw like this, or one could draw like this, or one could draw like this. Infinitely many lines that you could draw. And each one of those lines would produce residuals. And so you would have a sum of, you would have an SSE for each of those lines. The great math fact is that the regression line is the unique line out of all that you could possibly draw that's going to make that error sum of squares as small as possible. No other line you could draw other than that blue regression line would make that error sum of squares smaller. And there's a math way to find that minimizing line. And that's what is given to us by the lmGC method. So I just thought you might want to know where it does come from. We'll do another screencast where we look more deeply into how you can use the regression line to make some inferences about what the real nature of the relationship between the x and y variable might be.